We have applied so far Schrodinger wave equation to uh, a particle trapped in a one-dimensional box and a particle trapped in a three-dimensional box. Then we applied Schrodinger wave equation to two spectroscopic models called rigid rotator model and simple harmonic oscillator model. Today is our first attempt to apply quantum mechanics to understand the structure of atom. Okay, so today we will discuss the application of Schrodinger wave equation to the simplest element or atom known in the periodic table, that is hydrogen atom. And the discussion that we will do today is also applicable to hydrogen like ions, or we call hydrogen atom like ions. These are the ions that contain single electron like hydrogen. Okay, as I already told, hydrogen atom is the simplest atom that we can have in the periodic table, consisting of one electron revolving around the nucleus, which is nothing but a proton. So the application of Schrodinger wave equation to hydrogen atom enables us or helps us to deeply understand the structure of hydrogen atom. The understanding the structure of an atom, any atom, is very important for a chemist, because understanding the structure and the energy of an atom is very essential. Okay, and it is directly linked to understand the property of an element. Okay, so any material and its property is related to the property or the structure of the atom of which it is made. So for a chemist, understanding the structure of atom is very important. A lot of study has been done, okay, in order to understand the structure of atom. It is not a very recent work. From maybe almost 200-300 years, there has been repeatedly many theories proposed to understand the structure of atom based on the experimental results that were available at that time. However, the theories that were proposed, okay, had its own limitations, its own merit as well as its own demerits. The latest theory that was proposed before this application of Schrodinger wave equation to hydrogen atom is the Bohr's model. Okay, though Bohr's model of hydrogen atom has several merits compared to the earlier theories, there are as many as uh, demerits to the structure of atom that was proposed by Bohr. So to overcome those limitations, we required a theory, okay, that would well explain the structure of atom, in especially the hydrogen atom. So we will discuss about the application of Schrodinger wave equation to hydrogen atom, and how by solving the Schrodinger wave equation it is possible to get an understanding about the reliable structure of hydrogen atom. So first let us define a schematic of an hydrogen atom. As I already told, the hydrogen atom contains a positively charged nucleus, which is essentially nothing but the proton in the case of hydrogen atom, around which an electron is revolving. Okay, the electron is revolving. This is the simple picture that was given by Bohr. Okay, according to Bohr, the electron is revolving around the nucleus in a well-defined circular orbit. Okay, so what does it mean? It means that the radius of the circular orbit is fixed. The electron is revolving around the nucleus in a well-defined circular orbit. What does it mean? That the radius of the orbit is fixed, and it also means that once one knows what is the exact position of the electron, where the electron is revolving around the nucleus can be determined exactly. Okay, so this is the structure of atom that was given by Bohr. But in the quantum mechanical model of hydrogen atom, there is certain differences and some similarities in the structure that is proposed. Okay, as I already told, the hydrogen atom contains a positively charged nucleus around which the electron is revolving, and according to Bohr, the electron is revolving in a well defined circular orbit. But this proposition that the electron is revolving in a well defined circular orbit has some it possesses some serious uh, what can we say, it has certain limitation. Okay, it violates the Heisenberg's uncertainty principle. What is Heisenberg's uncertainty principle? It states that for a subatomic particle like electron, it is not possible to exactly find where the electron is. It means I cannot exactly pinpoint or locate the position of the electron, and therefore this well-defined orbit, the term called as well-defined orbit, is an exact violation of Heisenberg's uncertainty principle. So in order to uh, overcome this limitation, what we do in the quantum mechanical model is the electron is allowed to revolve around the nucleus, but the electron is not revolving around the nucleus in the well-defined orbit. We do not know where exactly the electron is, whether the electron is at a certain distance r from the nucleus, or it is at a certain distance r1 r2 from the nucleus. So we exactly do not know where exact the electron is, but what we know is this, that electron is revolving around the nucleus at some distance r, but what is the exact value of r, it cannot be exactly predicted. The exact value of r is not known. So the value of r is not fixed as proposed by Bohr. R is a variable. Okay, so what best we can do is in quantum mechanics is only to find out the maximum probability of finding the electron. Okay, we cannot find out the exact position of the electron, but we can find out where is the maximum probability of finding the electron. Okay, so this is the simple picture of hydrogen atom or hydrogen like ions that was proposed by uh, Bohr as well as the quantum mechanical model. The only difference I told you, the electron is not revolving in the well defined orbit, it is revolving around the nucleus in some orbit but not well defined. The another important limitation of Bohr's theory, it was almost a two-dimensional model, and we know that atom is not a two-dimensional entity, it is a three-dimensional entity. So the electron is not actually revolving in a circular orbit, it should be revolving around the nucleus on a sphere. It should be a spherical orbit. Okay, even the word orbit is not correct, because when I say orbit, it means it is a well-defined orbit, which is forbidden according to Heisenberg's uncertainty principle. The better word, okay, or the correct word that we have to use is what is called as orbital. What is orbital we'll see later. Okay, so the electron, so the atom is not a two-dimensional entity, it is actually a three-dimensional entity. So this picture is actually a three-dimensional picture. Unfortunately on this board I can only show a two-dimensional model. Okay, so this electron is not revolving around the nucleus in a circular orbit, but it is actually revolving around the nucleus on a spherical orbit or orbital. So the nucleus is at the center somewhere here. So I am imagining a sphere surrounding the nucleus, and the electron is revolving around the nucleus in some type of spherical orbit. Okay, now let Ze be the nuclear charge, where Z stands for the atomic number. Okay, Z is equal to 1 for hydrogen atom, and Z would be equal to 2 if I am considering a hypothetical helium plus ion. A helium plus ion like hydrogen atom contains only one electron. Okay, so in that case Z will be equal to 2. Or this model is also applicable for lithium 2 plus ion. Okay, I have removed two electron from a neutral lithium atom, which gives a lithium 2 plus ion. Okay, so this model is also applicable for lithium 2 plus ion because it contains only one electron. However, the value of Z for lithium 2 plus ion will be Z is equal to 2. Okay, so the value of Z is a variable depending on which atom I am discussing. If it is hydrogen, Z will be equal to 1. If it is helium plus ion, Z will be equal to 2. If it is lithium 2 plus ion, Z will be equal to 3. If it is beryllium 3 plus ion, okay, so these are hypothetical ions structures. Okay, we know that lithium 2 plus and beryllium 3 plus are highly unprobable ions. Okay, they do not exist under normal conditions. Okay, just they are hypothetical entities. So for beryllium 3 plus ions, if it really does exist, Z will be equal to 4. Okay, so Z is the atomic number. So Z into E would be the total charge of the nucleus. Okay, and the charge of the electron, you know that electron is negatively charged. So charge of the electron is minus E, where E is 1.602 into 10 to the power minus 19 coulomb. So you have two electric charges, okay, and there should be a force acting between the two electric charges, and according to Coulomb's law, that force is a force of attraction, because you have two unlike charges, that the two unlike charges attract each other, so there is a force of attraction between the two charged particles. And we all know that if there is a force acting on the particle, there should be a potential energy. If there is no net force acting on the particle, the potential energy remains constant, which we generally take as 0. But here, since there is a force acting on this electron, the force exerted by the nucleus, there is a potential energy, a varying potential energy. And what is the expression for such varying potential energy? According to Coulomb's law, okay, according to Coulomb's law, the potential energy for this type of structure is given by V is equal to minus Z into E square divided by 4 pi epsilon naught into R. Okay, so this is the expression for the potential energy for this type of system, which is obtained by using the Coulomb's law. As I already told you, Z stands for atomic number, E is the charge of the electron or the proton, okay, epsilon naught is called as absolute permittivity of a free space, and R, which is a variable, okay, we don't know what is the exact value of R. So R is nothing but the distance of the electron from the nucleus. Okay, now this potential energy that I have given by this equation 1 is called as spherically symmetric potential. Okay, so this is called as spherically symmetric potential. What is the meaning of spherically symmetric potential? The meaning of this is this type of expression, okay, for potential energy suggests that the potential energy V only depends on the distance of the electron from the nucleus. For example, if the electron is revolving around this circular orbit, or if it is revolving around a sphere at a distance r, wherever the electron is on that sphere or that circular orbit, okay, irrespective of the direction, okay, say for example the electron may be here, or the electron may be here, or the electron may be here. So wherever the electron is on the circular orbit, okay, the electron will be revolving around the nucleus, so the electron may be everywhere, it may be here also, so electron may be anywhere, okay, but irrespective of the uh, direction where the electron is, okay, whether it is in the horizontal direction or whether it is in the vertical direction, whatever is the direction of the electron, okay, that direction the electron makes with respect to the position of the nucleus, the potential energy only depends on the distance and not on the direction. For example, the potential energy experienced by the electron here will be same as the potential energy experienced by the electron here. It will be same as here, or it will be same as here. So whether the electron is here or here or here or here, it experiences the same potential energy. So the potential energy does not depend on the direction, it only depends on the distance. So for a electron on a particular spherical orbital or on a particular spherical or circular orbit, okay, the potential energy does not depend on the direction, it only depends on the distance of the electron from the nucleus. So that is why such type of potential is called as spherically symmetric potential. So whether the electron is here, whether the electron is here, whether the electron is here or here, wherever it is, it does not depend on the direction, it only depends on the distance. So that is why this potential energy is called as spherically symmetric potential. So this is a very important expression. We have obtained what is the expression for the potential energy of hydrogen atom or hydrogen like ions. Okay, now let us apply the Schrodinger wave equation. Okay, unlike Bohr's model, the quantum mechanical model is a three-dimensional model of hydrogen atom. The electron is revolving around the nucleus in three-dimensional space. it is revolving in some type sort of spherical orbital. So it is very apt or proper to use a three-dimensional Schrodinger wave equation. So let us first write the general three-dimensional Schrodinger wave equation. Okay, so the general three-dimensional Schrodinger wave equation is, okay, you can write like this: these dou square psi by dou x square plus dou square psi by dou y square plus dou square psi by dou z square plus 8 pi square m by h square into e minus b into psi is equal to 0. This is how we wrote Schrodinger wave equation. Now this term can be also written as del square psi or delta square psi plus 8 pi square m by h square into e minus b into psi is equal to 0. What is del square? Delta square is nothing but the Laplacian operator. Okay, we have studied all this at the beginning. Okay, so del square here is nothing but dou square by dou square plus dou square by dou y square plus dou square by dou z square is nothing but the Laplacian operator delta square. So you can use either this form of the Schrodinger wave equation or this form of the Schrodinger wave equation. I will be using this form. Okay, so this is the general Schrodinger wave equation where psi, which is called as wave function, it depends on the three variables, that is the position of the electron in Cartesian coordinate x, y and z. So what is V? Potential energy for the hydrogen atom. Already we know the potential energy of the hydrogen atom is given, or hydrogen like ions is given by this expression. So if I substitute equation number 1 in the general Schrodinger wave equation number 2, then we can get the corresponding Schrodinger wave equation for hydrogen atom. So to write the Schrodinger wave equation for hydrogen atom, what we should do? We should substitute this potential energy in equation number 2. So substituting equation number 1 in equation number 2 gives the Schrodinger wave equation for hydrogen atom or hydrogen atom like ions. It is given by del square psi, okay, del square psi plus 8 pi square m by h square into e minus of minus becomes plus ze square divided by 4 pi epsilon naught r into psi is equal to 0. Okay, where psi is psi of x comma y comma z. So what is equation number 3? It is a very important equation which you have to memorize, is the Schrodinger wave equation for hydrogen atom or hydrogen like ions. Okay, what is m here? Okay, we have to make certain changes. What is m here? That is very important. Okay, for that, what is m? We should first understand what assumption we are making, okay, when we are defining the structure of hydrogen atom or any atom. If we assume that, okay, the nucleus being very heavy is stationary, okay, you all know that the nucleus has the most mass of the atom. Okay, if you consider any atom, most of the mass of the atom is concentrated in the nucleus. The electron mass is very less compared to the nuclear mass. So generally what we assume that the nucleus being very heavy is at rest. So in that case the model is very simple. The electron revolving around the nucleus which is at rest. So it is only the electron which is revolving around the nucleus. In such case here m represents the mass of the electron. But is it really the nucleus stationary? The nucleus of an atom would have been stationary if it had infinite mass. Okay, but a nucleus, though it has mass much higher than the electron, definitely it is not having an infinite mass. So strictly speaking, in reality the nucleus is not stationary, it is also having certain types of motion. So it is not actually a single particle moving, it is a system of two particles. One is the motion, we have to consider the motion of the electron as well as the motion of the nucleus. And we dealt about a system containing two or more particles, okay, when we discussed the concept of reduced mass. So if a system contains more than one moving particles, what we do is we replace such a system by another system which is in fact a model. And that model, in that model you have one hypothetical particle which is moving, okay, and that hypothetical particle is having a reduced mass called as mu. Okay, here also you have two particles which are undergoing some type of motion, that is the electron, and the other particle is the nucleus. So what we do is we replace this entire structure by a model where there is one hypothetical particle of mass mu, okay, and that mu is nothing but called as the reduced mass. The reduced mass for this type of system is given by small m, that is the mass of the electron, into capital M, that is the mass of the nucleus, divided by m plus m. Okay, so m is the mass of the nucleus, small m is the mass of the electron. So this system which contains two particles is replaced by a imaginary system, a model where there is a single hypothetical particle whose mass is given by reduced mass mu is equal to mass of the electron into mass of the nucleus divided by mass of the electron plus mass of the nucleus. So strictly speaking, this m in this equation should be replaced by the reduced mass mu. So by doing that we get del square psi plus 8 pi square mu divided by h square into e plus z square divided by 4 pi epsilon naught r into psi is equal to 0. Okay, so this is also the Schrodinger wave equation for hydrogen atom or hydrogen like ion. The only difference is we have corrected that mass issue. Okay, here both are almost correct, but this is the exact way of representing Schrodinger wave equation for hydrogen atom, where we had made the correction with respect to the mass. Okay, so the mass is replaced by the reduced mass. Now this Schrodinger wave equation, okay, is represented in Cartesian coordinate. Okay, that is, here the position of the electron is expressed in terms of the Cartesian coordinate variables x, y and z. But since the motion of the electron around the nucleus is a rotational motion, okay, as we discussed in rigid rotator, it is always better to express the Schrodinger wave equation in polar coordinate rather than in Cartesian coordinate to describe rotational motion. So the rotational motion is better expressed in polar coordinates than in Cartesian coordinate. Okay, we have related Cartesian coordinate and polar coordinate when we discussed the rigid rotator, and also we learned about converting a Schrodinger wave equation from Cartesian coordinate to polar coordinate, okay, there itself. So we will not discuss those facts again here. Okay, so we will directly, what we will do now is we will directly convert this equation 4 which is written in Cartesian coordinate into another equation 5 which would be the Schrodinger wave equation for hydrogen atom expressed in polar coordinate. And why we are converting it from Cartesian coordinate to polar coordinate? Because the motion of the electron around the nucleus is rotational motion, and the rotational motion are always expressed, well expressed in polar coordinates instead of Cartesian coordinate. So let us rewrite equation 4 in polar coordinate. Equation 4 in polar coordinate is, okay, and when you convert this equation into a Schrodinger wave equation in polar coordinate, remember only the first term changes, the second term remains as such, okay, because only the first term here, del square, Laplacian operator del square, depends on x, y and z, that is the Cartesian coordinate. The second term does not depend on the Cartesian coordinate. So when we convert equation 4 into equation 5, the first term changes whereas the second term remains as such. So let us write the corresponding equation. It is 1 by r square into dou by dou r of r square into dou psi by dou r plus 1 by r square sin theta into dou by dou theta of sin theta into dou psi by dou theta plus 1 by r square sin square theta into dou square psi by dou phi square. Okay, so this term, which in fact contains three terms, dou square psi by dou x square plus dou square psi by dou y square plus dou square psi by dou z square, it is now transformed into these three terms written in terms of the polar coordinates. Plus, as I already told you, there is no change in the second term, so plus 8 pi square mu divided by h square into e plus ze square divided by 4 pi epsilon naught r into psi is equal to 0. What is psi? Okay, what is psi? Here psi is now expressed in polar coordinate variables r comma theta comma phi. R is the distance between the direct distance between the nucleus and the electron. Theta and phi are the angular variables which we had defined in our earlier discussion. Okay, so this equation number 5 is nothing but the Schrodinger wave equation for hydrogen atom or hydrogen like ions expressed in polar coordinate. Okay, so this equation is a partial differential equation containing three variables, and such type of differential equations can be solved by a method called as method of separation of variables. Okay, we have been using this method of separation of variables, okay, many times. So what is method of separation of variables? We are assuming that the overall wave function psi can be expressed as product of three functions: function of r into function of theta into function of variable phi. So that is the first and foremost essential step of method of separation of variables. So equation 5 can be solved by the method of separation of variables. Okay, according to this method, that is, the overall function psi of r comma theta comma phi can be written as product of three functions: function r depending only on variable r into function t depending only on variable theta into function f depending only on variable phi. Or in short, we will write it as psi is equal to r, okay, into t into f, where r is the shorthand for r of r, t is the shorthand representation for t of theta, f is the shorthand representation for function f of phi. Okay, if we substitute this equation number 6 in equation number 5 and make some mathematical rearrangements. What are those mathematical rearrangements? We will not discuss, it is out of scope of our discussion. Okay, we will only concentrate on some of the important steps. Okay, the detailed discussion, mathematical discussion, you will learn in your postgraduate level. Okay, so if I substitute equation number 6 in equation number 5 and make some simple mathematical rearrangement, what will happen is this three-dimensional equation, Schrodinger wave equation, will be converted into three one-dimensional Schrodinger wave equations. So this partial differential equation containing three variables, by applying, as a result of applying the method of separation of variable, will be converted into three one dimensional differential equation, each differential equation dealing with one variable, one differential equation dealing with variable r, one differential equation dealing with variable theta, the other differential equation dealing with variable phi. So what are those equations and what are the solutions to each of these differential equations? Let us see. Okay. So substituting equation 6 into equation 5, and after certain mathematical rearrangements, okay, and some mathematical calculations, okay, the three-dimensional equation 5, equation number 5, will be transformed or converted into three one-dimensional Schrodinger wave equations or differential equations, okay, each dealing with one variable, okay, each dealing with one variable. So one such equation that deals with variable phi would be, okay, the equation dealing with variable phi is d square f divided by d phi square plus, okay, m square into f is equal to 0. So this is the differential equation, okay, one dimensional differential equation which separates out of equation 5, which is a three-dimensional equation, and it deals with only one variable phi, and this is an ordinary differential equations which you can easily solve. Okay, we will directly write what is the solution. Okay, the normalized and acceptable, the normalized and acceptable wave function or the solution is, okay, the solution is f of phi, or you can simply write it as f, both are one and the same. So the function f, which is nothing but f of phi, is given by 1 by square root of 2 pi into e to the power I into m into phi. So when you solve this differential equation, you get this solution, that is function f is 1 by square root of 2 pi into e to the power I m phi. And remember, when you solve this differential equation, you have several boundary conditions. What are those boundary conditions? Their definitions we will not discuss. Okay, so we apply certain boundary condition which is applicable here, and we also apply normalization condition. After doing all those, we get this final equation. Here the value of m, okay, so m here cannot take all possible values. Its value is restricted to take only integral values, positive or negative integral values, including 0 up to infinity. Okay, and that is why this is called as magnetic quantum number. Okay, because this term or the quantity m can take only certain fixed values, not all values. That is why it is a quantum number which is called as magnetic quantum number. Why it is called as magnetic quantum number, you have already studied in your earlier undergraduate class or in your PU course, okay, when you studied Bohr's theory. Okay, and it can take only positive or negative integral values up to including 0. Okay, and there is no restriction on the maximum value it can take. It can take any value up to infinity. That is what this equation says. Okay, Similarly, when you apply equation number 6 into equation number 5, as I already told you, you get three separate differential equations. One equation dealing with variable phi. The second equation is an equation that deals with variable theta. Okay, and remember this equation is almost similar to the equation that we obtained in the rigid rotator model. Okay, now let us write an equation. Similarly, the equation dealing, okay, with respect to the variable theta, all these equations are very much similar to the equations that we had in rigid rotator problem. Why? Because the structure of hydrogen atom as we have defined and the rigid rotator, almost they are one and the same. So there also you have a lighter atom revolving around the heavier atom. Here also you have a lighter electron revolving around the heavier nucleus. So the expression for the equations, especially the theta equation and phi equations, are almost one and the same. The only difference between rigid rotator and a hydrogen atom is here you have one more extra variable, that is r, because the value of r, that is the distance between the electron and nucleus, is not a fixed. The electron can be anywhere, so r can take any value. But in the case of rigid rotator, we assume that the distance between the two atoms is fixed, so r was a constant there. So the differential equation contained only two variables, theta and phi. But here in the hydrogen atom we have one additional variable, that is r, including theta and phi. Nevertheless, the equations of with respect to theta variable, which I am going to write now, and the phi variable are one and the same in both rigid rotator as well as hydrogen atom. So the equation that deals with variable theta, okay, this is the final equation I have written after doing lot of mathematical work. Okay, so 1 by sine theta into d by d theta into sine theta into dt by d theta plus beta, which, okay, what is beta we had learnt in earlier when we discussed rigid rotator. So similar type of definition is applicable here. Beta minus m square divided by sine square theta into t is equal to 0. So this is the one-dimensional differential equation, a Schrodinger wave equation dealing with variable theta. So remember, see here, notice that in equation 7 or in equation 9 we have ordinary derivative. Why we have ordinary derivative? Because we are only dealing with the one variable, whereas equation number 5 we used partial derivative, dou square by dou r square, like that, dou square by dou theta, dou by dou theta, like that, because it is a differential equation containing three variables where we have to use partial differential equation. And if you solve this differential equation, again, how to solve this we will not go into the discussion. The solution to equation 9, okay, solution to equation number 9 is given by, okay, an expression which you are familiar with, okay, because the same expression holds good for rigid rotator. So t is equal to square root of 2 into L plus 1 into L minus mod m factorial divided by 2 into L plus mod m factorial, okay, into a polynomial p, a function p, which depends on the value of L, okay, degree L and order of mod m into cos theta, and further you can show that the value of beta is equal to L into L plus 1. So the only difference in the expression that you wrote in rigid rotator and the equation that I have written here is, okay, this symbol L, okay, there we used the symbol J, here we are using the symbol L, okay. J represented the rotational quantum number in the case of rigid rotator. So here you have an analogous term, okay, a similar value, a similar quantity represented as L, which stands for azimuthal quantum number, okay. So the L in this equation is nothing but the azimuthal quantum number. Okay, azimuthal quantum number. M, you know, it is the magnetic quantum number. P we had defined in the rigid rotator, which is a function or a polynomial called as Legendre function. Okay, Legendre function. Now when boundary conditions are applied when solving this differential equation, what it makes is it restricts the value of L. Okay, the value of L is restricted. L can take on values. Okay, it can take on values, integral values starting from 0, but only positive values. Okay, so positive integral values. Why it takes only restricted values? Because this is because of the boundary condition, and there is no limit on the maximum value. It can take value, any value, up to infinity. But when we are solving this differential equation and applying the boundary condition, what happens is there is one more restriction on the value of m. Okay, there is already a restriction on the value of m, that it can take only integral values. Now when we solve this differential equation, there is an addition restriction on the value of m. What is that additional restriction is m, of course it takes only positive or negative integral values including 0, but the maximum value it can take is plus or minus L. Earlier, though the value of m is restricted to take integral values, but there was no limit on the maximum value. Okay, but here the maximum value m can assume or take is plus or minus L. So this restriction is due to the additional boundary condition that we have when we solve equation number 9. Okay, the equation number, okay, I will write the other equation and then I will stop. So this is the one dimensional equation with variable phi. This is the one dimensional equation with variable theta. You have one more additional differential equation dealing with variable r, and that equation is very important for hydrogen atom. That equation was missing in the rigid rotator because r was not a variable there, r was a constant. But in hydrogen atom the variable r is very important, because from that function we can find out what is the possible distance of the electron from the nucleus. Okay, so by applying the method of separation of variable, you get the third equation dealing with variable r. Okay, so the equation dealing with the variable r is, okay, you have to memorize all these equations. Unfortunately they are complicated. 1 by r square into d by dr. See, again I am using ordinary derivative because there is only one variable, into r square into dr by dr plus 8 pi square mu into 8 pi square mu divided by h square, okay, into e plus z square divided by 4 pi epsilon naught r minus beta divided by r square whole multiplied by r is equal to 0. Okay, so this is the differential equation dealing with variable r. As you can see, it is a quite complicated differential equation. Of course it can be solved, okay, by using some complex mathematical procedures. Fortunately we need not go into the detailed procedure of solving this differential equation. We will write the final solution. Okay, unfortunately the final solution is complicated, so you have to memorize that expression. Okay, so the normalized and the acceptable solution to equation number 10 is r, which is nothing but r of r is equal to square root of 2 into z divided by n into a naught whole cube into n minus l minus 1 factorial whole divided by 2 into n into n plus l factorial whole cube into outside the bracket e to the power minus rho divided by 2 into rho to the power l into, okay, the things is becoming more and more complicated, okay, into l, a function l which depends on the azimuthal quantum number l, and it also depends on n plus l and 2l plus 1, okay, 2l plus 1. What is the exact meaning of each and every term is not detailed, is not required in detail, okay. I think I missed the equation number. This is equation number 11, this is equation number 12, okay. So which are the known and unknown terms? Let us see. Z is already known, it is the atomic number. N here is nothing but the principal quantum number. Okay, it's called as principal quantum number. It is again a quantum number that arises because of certain boundary conditions that exist while solving this differential equation, and the allowed values of n are n can take any integral values, okay, from 1 2 3 and so on. It can take any positive integral values, it cannot take n equal to 0, okay. What is the reason why n cannot be taken as 0? The reason is almost similar to the one we gave in particle in a one-dimensional box. Remember, in a particle in a one-dimensional box, n cannot be equal to 0. So a similar reason can be given here why n cannot be equal to 0. So n starts from 1 and it can take all positive integral values. However, the boundary condition that arises here, it inserts another restriction on the value of L. Remember, when we solved equation number 9, the allowed values of L were 0 1 2 3 etc. There was no limit on the maximum value that L can take, but here we observe that there is a restriction on the maximum value of L. So L can take integral value 0 1 2 3 etc., but the maximum value it can take is only n minus 1, okay. And the reason is very simple why it can take only n minus 1, which will not go into those discussions. Remember, the L can take only values 0 1 2 3 with maximum allowed value equal to n minus 1, and the rho which I have used here is defined as rho is equal to 2 into z divided by n into a naught, okay. What is z, what is n is already known. What is a naught in this equation is a naught is equal to h square divided by 4 pi square mu into e square, okay. A naught is given by h square, h is Planck's constant, 4 pi square mu, that is the reduced mass of the system, into e square, okay. So that is the definition of a naught, and this a naught is called as Bohr's radius, okay. This a naught is nothing but called as Bohr's radius, okay. It is nothing but the radius of the first circular orbit of the hydrogen atom according to Bohr's model, okay. A naught represents Bohr's radius, which is nothing but the radius of the first or the ground state circular orbit, okay, of the Bohr's model of hydrogen atom. And if you substitute all these known values, you can calculate the value of a naught, which is a naught is equal to 0.53 angstroms, okay, 0.53 angstrom. And this symbol L, it is a polynomial called as Legure polynomial, okay. This L is a polynomial called as Legure polynomial. Again, what is the expression for that polynomial is out of scope of our discussion, okay. Just remember that this is a mathematical polynomial called as Legure polynomial. So equation number 12 is the acceptable and the normalized solution or the expression for the wave function containing variable r. And now if we multiply the three acceptable wave functions, okay, we have three wave function, one wave function dealing with the variable r, another wave function dealing with variable theta, and the earlier wave function, okay, which I have rubbed now, okay, in the previous slide we had it. So the wave function dealing with variable phi. So if I multiply all the three wave function in accordance to equation 6, okay, then it is possible to write the overall or the total normalized acceptable wave function, okay. And along with that, you can, if you go back to the equations that I have written for each variable, okay, refer back to equation number 7, which deals with the variable phi, refer to equation number 9, which deals with variable theta, and refer to equation number 11, which deals with variable r. Okay, if you carefully look at these three differential equations, you can observe that the term energy E appears only in the variable R. So what does it mean is the total energy of the electron revolving around the nucleus, okay, for a hydrogen or hydrogen like ion, okay, it depends only on the distance of the electron from the nucleus, or it depends only on the principal quantum number, and it does not depend on the angular variables theta and phi, okay. Because energy term appears only in equation r, it means that the energy of the electron depends only on the quantum number that arises from this equation, and it is the principal quantum number that arises from this equation. So the total energy of the electron only depends on the principal quantum number n, okay. So it can be shown that the energy of the electron, okay, revolving around the nucleus depends only on the principal quantum number and is given by the total energy, okay, is given by E n is equal to, because the energy depends on the principal quantum number n, so it depends on the distance of the electron from the nucleus, and it also depends on the principal quantum number, is given by minus mu z square e to the power 4 divided by 8 epsilon square h square into 1 by n square. So this is the expression for the total energy of the electron revolving around the nucleus of hydrogen atom or hydrogen like ions, okay. And from this equation it is very clear that the energy depends only on the principal quantum number, it does not depend on the other quantum number. Why? Because the energy term appears only in this equation dealing with variable r, and when you are solving this differential equation, it gives rise to principal quantum number. The other quantum numbers L and M does not arise because of this equation, they arise because of the solution of theta and phi equation, okay. And this expression that I have written here, okay, is very much similar to that is given by Niels Bohr, okay. So Bohr, in his Bohr model, he obtained an expression for the energy, and that expression for energy is similar to the expression that we obtained by applying Schrodinger wave equation to hydrogen atom. So the equation given for energy are similar by the quantum mechanical model of hydrogen atom as well as Bohr's theory. And as we can see here, all these are constants, okay, for a given atom. The energy of the electron depends on the value of quantum number, and since the value of n is restricted to certain values, the energy of the electron is also restricted. So we can say that the electronic energies in an atom are quantized. The electronic energies in an atom are quantized. Let me end this class by writing the overall wave function. Okay, the overall normalized wave function of hydrogen atom or hydrogen like ions is given by, okay, again we'll go back to the method of separation of variable, which is psi of r comma theta comma phi. This is the overall wave function, but according to method of separation of variable, the overall wave function is r of r into t of theta into f of phi, and we have already found out the expression for this function. Okay, r of r is given by equation number 11, sorry 12. T of theta is given by equation number 10, and f of phi is given by equation number 7, so sorry 8. So if I multiply all these three terms, that would give, the overall expression for wave function, and it is, okay, I will write the overall expression for wave function, which is nothing but the multiplication of wave function with the theta variable, r variable and phi variable, which you have to memorize. Okay, so it is therefore psi of r comma theta comma phi is equal to 1 by square root of 2 pi into e to the power I into m phi, which is nothing but function f of phi into square root of 2 into L plus 1 into L minus mod m factorial divided by 2 into L plus mod m factorial into the polynomial of degree L and order m into cos theta. This is nothing but t of theta into the function dealing with variable r, that is square root of 2 into z divided by n into a naught whole cube into n minus L minus 1 factorial divided by 2 into n plus L factorial whole cube into e to the power minus rho by 2 into rho to the power L into a polynomial L depending on the variable rho and also depending on n plus L and 2n plus 1. So this is the expression, equation number 14, a very lengthy expression, which is the solution or the expression for the wave function for the simplest known atom, that is the hydrogen atom or hydrogen like ions such as helium plus, lithium 2 plus or beryllium 3 plus. So equation number 14 you have to memorize. This is the total or the overall wave function for hydrogen atom or hydrogen like ions. It depends on three variables, phi, theta and r. R is contained in this expression. Okay, so this is about the application of Schrodinger wave equation to hydrogen atom. We have obtained an expression for energy and also obtained an expression for wave function. Of course, we have avoided all the mathematical derivations and we have only taken some of the important steps. Now in the next class we will discuss some more points about the wave function for hydrogen atom, especially the radial part of the wave function we will concentrate. Okay, the angular part you already know the shapes of s orbitals, p orbitals, d orbitals. I will not discuss that here. We will only concentrate on the radial part of the wave function. Okay, thank you.